If your air conditioner stopped working tomorrow, how long would your house remain livable? Not comfortable, livable. A few hours, maybe a day. After that, the temperature inside would begin to rise, slowly at first, then aggressively. Walls would trap heat, air would stagnate, and the system you rely on to make your home habitable would reveal something uncomfortable. It was never designed to work without constant power. Now imagine a different kind of structure, one that doesn't need an air conditioner, not because it has a backup system, but because it was never designed to require one in the first place. A building that stays cool in extreme heat, not through machines, but through design. That building already exists, and it existed long before electricity. More than 1,000 years ago, in one of the hottest environments on Earth, entire cities were built without mechanical cooling. Temperatures outside climbed past levels that would overwhelm modern homes. And yet, inside, the air remained cooler, stable, breathable. The secret wasn't hidden underground, it was standing in plain sight. Tall structures rising above rooftops, built from clay and brick. They weren't decorative, they were functional. Precision-built systems designed to capture wind, direct airflow, and regulate temperature. These were wind catchers. At first glance, they seem simple, a tower with openings facing different directions. But inside, the design becomes more complex. Vertical shafts channel air downward into living spaces. When wind is present, it is captured at elevation, where speeds are higher, and directed into the structure below. That alone creates airflow, but the real system doesn't rely on wind, because even in still air, these towers continue to function. When the sun heats the outer surface of the tower, the air inside begins to warm. Warm air rises. As it moves upward, it creates a pressure difference at the base of the shaft. That pressure pulls cooler air from lower areas, often from shaded courtyards or underground spaces, into the building. The structure begins to breathe, not through mechanical fans, but through physics. And this is where the second principle comes in: the earth. Beneath your feet, temperature behaves differently than it does at the surface. As you go deeper into the ground, temperature fluctuations begin to disappear. At a certain depth, the temperature stabilizes, remaining nearly constant throughout the year. In most regions, this stable temperature sits far below peak summer heat. That means the ground itself becomes a cooling source. Ancient builders understood this. They didn't just build on the land, they built into it. Walls were partially buried, entire structures were carved into hillsides. Underground chambers were integrated into the design, not as storage, but as climate control. Air passing through these spaces would naturally cool before entering living areas. The result was a system where the building pulled cool air from the earth and expelled warm air through vertical channels. No electricity, no moving parts, just temperature differences driving airflow. And when you combine these two systems, wind capture and ground cooling, you get something remarkably effective. A structure that regulates its own temperature, continuously, predictably, reliably. And this wasn't limited to one region. Across different civilizations, similar principles emerged. In parts of China, entire communities lived in dwellings carved directly into the earth. These structures maintained stable internal temperatures regardless of extreme external conditions. In parts of Europe, thick stone buildings absorbed heat during the day and released it slowly at night. Underground cities in other regions used depth and airflow to maintain livable conditions without external energy. Different cultures, different materials, same principles. Use the earth as a thermal buffer. Use vertical airflow to move heat. Don't fight the environment, work with it. Now compare that to modern construction. Today, most homes are built with lightweight materials, walls that react quickly to temperature changes, structures that heat up fast and cool down just as fast. Instead of storing energy, they depend on it. Heating systems compensate for heat loss, cooling systems compensate for heat gain, and both require constant input. Remove that input, and the system fails. But when a building is designed differently from the beginning, that dependency disappears. The structure itself becomes the system. And this brings us to something important, because none of this is theoretical. Modern research has measured these effects. Temperature reductions from passive airflow systems, energy savings from earth-integrated designs, stability achieved without mechanical intervention. This is not outdated knowledge, it's validated, and yet it's rarely applied. Not because it doesn't work, but because it doesn't fit the current model. Modern construction prioritizes speed, standardization, and compatibility with existing systems. Materials are selected for convenience, designs are simplified for mass production, and systems are added afterward to compensate. Instead of designing buildings that regulate themselves, we design buildings that require regulation. That difference changes everything, because it determines whether a structure can function independently or whether it depends on continuous external support. And once that dependency is built in, it becomes difficult to remove, which is why these older systems feel so different. They weren't designed for convenience, they were designed for resilience, for conditions where failure wasn't acceptable, where survival depended on performance, and that mindset produced buildings that behave differently, not just in how they look, but in how they function. Now here's where things become interesting, because these principles aren't locked in the past, they can be applied today. A modern structure can still use earth sheltering, it can still integrate airflow systems, it can still orient itself to capture or avoid solar energy depending on the season. The materials may change, the designs may evolve, but the physics remains the same. And that means the opportunity still exists, not to copy ancient structures exactly, but to understand why they worked. And then apply those principles in a way that fits modern needs. Because the goal isn't to go backward, it's to build better, to create structures that require less input, that maintain stability without constant intervention, that work with their environment instead of resisting it. And once you start thinking that way, the entire concept of a building begins to change. It's no longer just a space you live in, it's a system, one that manages temperature, airflow, and energy through design, not through consumption. And that shift is what makes these ideas powerful, because they challenge the assumption that comfort requires constant energy. They show that under the right conditions, design can replace dependence. And that realization leads to a different question. Not whether this works, but why it isn't more common. Because the knowledge exists, the research exists, the examples exist, across history and in modern applications. The only thing missing is awareness. And once that changes, so does the way we build. If this changed how you think about cooling, energy, or even the purpose of a building, subscribe. Because the next system might not just reduce your energy use, it might eliminate the need for it entirely.